In Unit 6, we start to talk about chemical reactions and how to model them using chemical equations. So the chemical reaction is what we would actually see if we were performing this in a lab, while the equation is the written form that represents what's going on in that reaction. So our aim for this section is to first learn the signals that show a chemical reaction has occurred. So this is going to help us to determine what to write down when we're taking the information that's given to us in a statement and trying to transform that into a chemical equation. So there are certain keywords inside in equations that we need to look for to be able to help us do that. So in evidence of reaction, we're looking for the same thing that we looked at when we were talking about chemical changes. So remember, chemical changes were a way for us to know that a substance had been changed from one thing to another. So when something changes chemically, we know it's not the same compound anymore. Every compound has certain physical characteristics or physical properties. When those physical properties change, we're not talking about the same substance anymore. So that tells us that something new has been formed. So we talked about a color change. When we start with something that's colorless and we mix it with something else and it has a color, or vice versa, it starts a color and then changes to something that's colorless, that's an indication that since those physical properties have changed, the substance has also changed chemically. Heat being produced or absorbed. So this is not adding heat to a system. This is if we mix two things together, then what happens is heat can be released as a result. And sometimes, and you can do this at home, if you have Epsom salts and you pour those Epsom salts in water, you'll find that it actually gets cooler. So heat is absorbed in that process. When a solid forms, and we talked about this a little bit, but this is what we call a precipitate. So when we're taking two aqueous or liquid solutions, and then we are mixing them together, we can start with clear, colorless solutions, and then we can end up with a solid forming in those solutions. And that usually looks like a powdery substance or a very thick cloud that appears in those solutions. So that's called a precipitate. That's something there that wasn't there in the beginning. And then also bubbles form. So we've talked about vinegar and baking soda, how we know when we mix vinegar and baking soda together, we end up with a lot of bubbles, and those bubbles are carbon dioxide gas. And that carbon dioxide gas wasn't there in the beginning. So if we end up with something at the end of a reaction that wasn't there in the beginning, we know a chemical change has occurred, and then we can represent that by writing down a chemical equation. In our next section, our aim is to learn to identify the characteristics of a chemical reaction and the information given by a chemical equation. So again, this just goes a little deeper into reading through a statement and trying to figure out the parts of that statement, what they mean, and how they're going to be compiled in a chemical equation. So in what order to write them down in, what the different symbols mean, and how to transform that from a statement to an actual equation. So looking at this statement, or rather this chemical equation, we want to know what information can we get from this. So there's a lot of things just in this statement. So for example, this first side, actually we can separate this into two sides and we get two different pieces of information out of this. We know that these are the reactants. These are what exist before the reaction takes place. We also know that these are the products. These are produced through the course of the reaction. They're what are made or what is made after the reactants actually react. So then there are formulas on the left and the right, and we can name those to come up with a statement, but for right now, we're just concerned with the basic setup of a chemical equation. So this plus symbol, this can mean a few things, or we could see a few statements that clue us into the fact that that plus sign should be there. One of the most common ones is and. So I might see CH4 and O2. I might also see the words reacts with, CH4 reacts with O2. I might see combines with. And all of those things are acceptable. They all mean the same thing. They all mean that these two different reactants are coming together. This this arrow can mean to form. So I might say CH4 reacts with O2 to form. I can also use the word yields. So you've probably seen a yield sign on the road, and a lot of people think that that yield sign means stop, but it really means to give way to. So you are to sit there until your path is clear. And when you do that, you're giving way to all of these other things to be able to actually form or to go ahead of you. So yield is another word for produces. So we can also say produces or produce. So we could say CH4 and O2 produce. And then we have CO2 and H2O as our product. So this plus sign also means and on the other side. However, it doesn't mean reacts with anymore. So if we see reacts with, we know that's only referring to what we're going to see on the reactant side, not the product side. Another thing we might see on this side is the term byproduct. So one way of wording this might be CH4 plus O2 yield CO2 and H2O as a byproduct. It just means an additional product. So once we get these key words down, then that's what helps us to put these reactants and products on the correct side. Sometimes, and not in an attempt to trick you, but sometimes what you might see is CO2 and H2O are produced from, and then you are still expected to know that those are on the product side of a reaction. So in the same way that we read a periodic table from left to right, we also read a chemical equation from left to right. So I could say CO2 and H2O are produced by the reaction of CH4 and O2, and that doesn't mean I'm going to write CO2 and H2O first, because I'm still using the word produced by in there. So I still have to make sure I'm putting them on the correct sides of this arrow. And the arrow always, at least at this point, the arrow will always point from left to right. So now assume at this point that we've been able to take our statement and put the reactants and the products on the correct side, and we were able to put the plus signs in the correct locations. Is anything missing at this point? We need to represent certain states of matter because, as we know, something like H2O can exist in solid, liquid, or gaseous form. And the state of matter is really dependent on the conditions or the specific wording given in the statement. So if you're told that you're dealing with water vapor, you know that water is going to be a gas instead of a liquid. So our states of matter, at least the ones that we're concerned with that we can deal with in an equation, are going to be solid, and solid states of matter are written with lowercase letters in parentheses right after the compound. And I'll show you what that looks like in a second, but we know we have solid, we have liquid, we have gas, and everyone thinks plasma is next, but what is actually next is what's known as an aqueous state, and this is AQ. Aqueous means dissolved in water. So anytime you see a liquid that is not pure, and you will be told you have something like a sodium chloride solution. If you're told you have a solution, that means you're referring to something that's dissolved in water. And in that case, it's aqueous. Water cannot be aqueous. And that's because if I have water, and I'm assuming it's aqueous water, that means water is dissolved in water. And if water is dissolved in water, I have a pure liquid anyway. So this would refer to something that is a pure liquid, not something that's dissolved in something else. So just know that aqueous means dissolved in water. Another thing you should know about the aqueous state is that all acids exist in aqueous form. So if we have to represent the state of an acid, it can only be in aqueous form. Some of these we know, and we know by their position on the periodic table. We know that oxygen is gas, and it's O2 for a reason, and we will talk about that shortly. And CO2, depending on what temperature we're at, if we're at room temperature, we know we have to be talking about gaseous CO2. So depending on the conditions you're given, you will be told which state that you're talking about. If it's a substance we haven't discussed, I do not expect you to know what state of matter that you're talking about. So the first one we're looking at is an example of a statement you will be given that you now have to turn into an equation. So we want to be able to list reactants. We want to be able to list products. We want to be able to indicate where the pluses go. And then we also want to give states of matter. And there's another piece to this that we're going to look at in the next section, but here we're just looking at setting up the equation correctly. There's a lot of different pieces to this, so we want to separate these out as we go. Solid potassium is the first thing that we want to look at. So if we look at the periodic table, we should know where potassium is, but if you don't, potassium has the symbol K. So that's what we put as the first part of our equation. The solid tells us the state. So we can say solid potassium. The next part is reacts with. Remember, reacts with means plus. And then we have water. We know water, dihydrogen monoxide or H2O. And if we're being told water, we can assume water is just liquid. We're not being told water vapor. We're not being given conditions to assume that we're above 100 degrees Celsius and that we have water vapor, or that we're below zero and we have solid water. We're just being told water. And then we have to form. Remember, to form is the arrow. And then we have hydrogen gas. So this is where we have to be familiar with what are called diatomics. Diatomics are elements on the periodic table that always come as twos. So if you look at your periodic table, you will be able to identify where these are by their position. And there's a few different ways to remember this. So on your periodic table, you will see the position of the different diatomics. So in this one, we're going to start with nitrogen, and we're just going to draw something that looks like a 7. And that is to remind us that there are 7 diatomic elements, which means when we write these diatomics in a chemical equation, we are going to write them as 2. And that's only when they appear by themselves. So if you're told something reacts with nitrogen, you are going to write it down as N2. Also O2, F2, Cl2, Br2, and I2. Now, if we count these up, we have 1, 2, 3, 4, 5, 6, and the 7th, although cut off slightly, is actually hydrogen. So looking at your periodic table, you should be using one of these on your test anyway. Draw the shape of a 7, starting at nitrogen, ending at iodine, and know that it's going to point to hydrogen as your 7th. There are other ways to remember this also. One of the ways is to say that you are going to have no fear of ice cold beverages, or some people might say Breer, to remind yourself which elements you're looking at, because the first letter of each of these words is going to give you a hint as to one of the polyatomics. The other way to do it is a word that just makes my skin crawl, but it seems to help most people. And we would pronounce this word Hofbrinkel. Now, with this word, it's actually kind of nice because what it does is, instead of saying something like beverages or beer, if you know what that is at this point, or even C in cold, it doesn't just give you the C in cold, it lets you know that the Cl is the element chlorine, not the element that we would not the symbol that we would use to represent the element carbon. So it is your job to be familiar with which elements are diatomic, and then to make sure that you are representing that in your chemical equation. So we left off talking about hydrogen gas. So when we're talking about hydrogen gas, we are putting an H2 followed by a G. Hydrogen is our compound, in this case, two elements together. We're talking about elemental hydrogen. So we are talking about H2 because it is mentioned by itself. And gas. They told us it was in gaseous form, so we're putting a G symbol next to the hydrogen. And then we see this and term again. Remember that means plus. Potassium hydroxide. So this goes back to last chapter when we were looking at taking the names of these compounds and putting them into their chemical formulas. We know potassium is K. Hydroxide, if we look on our polyatomic ion list, we will see that that's OH. Now we need to look at the periodic table to be able to get the charges for these. Potassium is right here on the left side of the table, and we know everything in this column has a charge of +1. So we're looking at potassium with a +1 charge. Hydroxide has a -1 charge. So since these are already in a 1-to-1 ratio, our compound is simply KOH. And since it says it is dissolved in water, we know that means we are dealing with an aqueous compound. Take a minute to try this one on your own, and we will talk about this together. Solid mercury 2 oxide is the first thing that we have to represent. So mercury, we know from the table, is Hg. 2 means it has a +2 charge, and oxide means oxygen, and we know from oxygen's position on the table right here that it has a -2 charge. So that's how we're going to come up with our formula. So mercury 2 oxide gives us the formula HgO. It tells us that it's solid, so we're going to put solid in parentheses. And then we see this word decomposes. Now we know decomposes refers to something breaking down. So that means that mercury 2 oxide is our only reactant. And that's going to break down, and we can even include this part here, decomposes to produce liquid mercury. And again, if they mention an element by itself, we're just listing the element and that's it, unless it's one of our diatomics. Now, if we were to recognize this as a diatomic, we would have to put a 2 on the outside. But we are told that we are dealing with liquid mercury, which means we have to put an L in parentheses after mercury. Again, we see the term and, which means plus. And then we see gaseous oxygen. So gaseous oxygen tells us we're dealing with O, and we know that oxygen, when it's by itself, so that's why there was no 2 at the base of oxygen here, because it was not by itself. But when oxygen is produced by itself, we know it's diatomic, so we're going to put the 2 down at the base, and then we know, according to our statement, that it's gaseous. Try this one, pause, and then we'll come back together to review it. So here we have solid carbon. Carbon, we know, is just C. It is not diatomic, but they do tell us that it's solid, so we're going to put solid in parentheses. They tell us reacts with. We know reacts with means plus. Then they tell us oxygen. Oxygen, we know, is O, and we know oxygen by itself is diatomic, so it is going to have a 2 next to it. Now, you do not have the periodic table where we were able to specify states. So for our purposes, I will be giving you all of the states you need in the equation to be able to balance or to write the correct equation, unless I tell you otherwise. So like I told you, acids are aqueous, so you are expected to know that acids are aqueous. But every other time, I will be telling you the state. So we know here that oxygen is gaseous. And then we see 2 form. And then we see gaseous carbon dioxide. So we know from the last chapter, carbon dioxide is CO2. they told us it was gaseous. Try this one, pause, and then come back. For this one, we have solid magnesium. So if we are able to find magnesium on the table, we can see that it's Mg. Please don't confuse magnesium and manganese. Manganese is Mn, magnesium is Mg. It happens all the time. Solid is S. Reacts with is plus. Liquid water, H2O, L. And then we see two form. We know two form means the arrow. Solid magnesium hydroxide. So we know that according to the periodic table, again, this is just from how we were able to label the columns based on the number of valence electrons and the charge they would form, that magnesium has a charge of +2. We know hydroxide is OH, both capitalized with a charge of -1. So if we put parentheses around the base of our polyatomic and we make a formula out of this, we will end up with Mg and in parentheses OH and a 2 on the outside. And then we see and, which means plus, and then we see hydrogen gas. We know hydrogen is one of our diatomics, so we have H2 and G. So the only thing that we forgot to do here was specify the state on magnesium hydroxide, and they told us that right here, so we know magnesium hydroxide is solid. So just double check when you're done. Are all your formulas correct? Make sure all your charges have disappeared. Make sure you have the same number of elements on both sides, and make sure you've specified states. Here's another one. Take a minute. So the first thing they tell us is solid ammonium dichromate. We know ammonium on your polyatomic ion list. This is the only polyatomic cation that we have. NH4 with a +1 charge. We have dichromate, which is also on your list. This is Cr2O7 -2. So when we put this together in a formula, I want to put parentheses around the polyatomic cation this time. So we have NH4 with a 2 on the outside, Cr2O7, and they told us this was solid. Then they tell us decomposes too. So that means it's our only reactant. If we see that something decomposes, that is the only thing that's there. That's a reaction in itself. Solid chromium 3 oxide. So we know the symbol for chromium, if we look at our table, is Cr. The 3 tells us that we have a charge of +3. Oxide is oxygen with a charge of -2. And when we put this together, we get Cr2O3. And this tells us that we have gaseous nitrogen, and we need to look a little bit ahead here just to see which side this is going to go on, and gaseous water. And then again, we see this term byproducts, which means those also exist on the product side of this reaction. They did tell us we have solid chromium 3 oxide with gaseous nitrogen. We know nitrogen is one of our diatomics, so we're going to say N2 gaseous, and gaseous water. We could have also said water vapor to mean the same thing.